Bismillahirrahmanirrahim. In this lecture, we will be dealing with the understanding of analysis, design, and control of distillation column. Distillation is one of the most important operation in chemical sciences and also one of the most challenging operation to design and control. So basis of distillation is phase equilibrium, especially vapor liquid phase equilibrium. So the distillation is a process of separating the component from a liquid mixture by using a selective boiling and condensation. Distillation is one of the most common separation technique which is being used in various analytical processes. So this distillation includes two phenomena. Number one is selective boiling and condensation. So the mixture will be boiled at a selective temperature and it will involve the subsequent condensation of the component which is in the vapor phase from the liquid mixture. So this distillation is a separation technique that can be used to either increase the concentration of a specific component in the mixture or to obtain pure component from the mixture. So the process of distillation actually is the difference in the boiling point of the component in the liquid mixture by forcing one of them into the gaseous state. So this process of distillation is based on the fact that the vapor of a boiling mixture will be richer in the components that have lower boiling points. So the vapor will contain a lot of components that have lower boiling point, while the liquid mixture contains abundance of molecules or components that have higher boiling point. So these components that will remain in the liquid mixture, they will not be affected by the selective boiling point. Those molecules which have close boiling point in accordance to selective temperature that has been given to the molecule, they will evaporate and becomes vapor. So the molecules with lower boiling point will be in abundance in the vapor state in the upper part of the container. There are different types of distillation, such as simple distillation, which involves heating the liquid mixture to the boiling point of a specific component and subsequent condensation of that gaseous phase of that component to convert this vapor into the liquid phase. So this simple distillation involves the process of vaporization and condensation. Number two is a fractional distillation, which is used to separate mixture of liquids that have a very close boiling point. Third one is steam distillation, that is used to separate heat sensitive component from the mixture. Number 4 is vacuum distillation, and this vacuum distillation is ideal for separating mixture of liquid with very high boiling points. Fifth one is a air sensitive vacuum distillation, and this is used for those compounds that are sensitive to air and readily react with the air. So the vacuum distillation process is carried out, but in this vacuum distillation, vacuum is replaced with an inert gas. Once the process is complete, such process is often known as air sensitive vacuum distillation. The sixth one is short path distillation, and it is used to purify a small quantity of the compound that is unstable at high temperature. So this is done under the lowered pressure level. Seventh is zone distillation. And the process of zone distillation involves the partial melting of a substance and the condensation of the resulting vapor to obtain a pure distillate, and this is carried out in a long container with the help of zone heater. This is a schematic diagram of the phenomena of distillation. Distillation actually involves several vaporization condensation steps which is taking place in the distillation column. So these apparatus that are shown here, round bottom flask or a distilling flask will be required, a source of heat, most commonly a hot plate is used to provide a sufficient amount of energy to vaporize the liquid molecule from the liquid mixture, a receiving tank to collect the condensed vapor, and a thermometer which is used to measure the temperature in the distillation column, and a condenser which is used to condense the vapors that were separated from the liquid mixture. The temperature at which vapor pressure of a liquid becomes equal to the pressure of the surrounding area is called boiling point of that liquid. So at this temperature, the liquid is converted into its vapor form via the formation of vapor bubbles at its bulk. It is important to mention here that the boiling point of the liquid changes with the pressure applied on it. For example, the boiling point of water at sea level is 100 degrees Celsius. However, its boiling point is 93.4 when the pressure is relatively lower at high altitude. Vaporization is a phase transition of an element from its liquid phase to the gaseous phase in the form of vapor. So this vaporization and the process of distillation is dependent on Dalton's and Raoult's law. As the Raoult's law states, the partial pressure of a single liquid component in an ideal liquid mixture equals the product of the vapor pressure of the pure component and its mole fraction. While according to the Dalton's law of partial pressure, the total pressure exerted by a mixture of gases is equal to the sum of partial pressure of all the constituent gases. This vaporization involves two major phenomena. Number one, evaporation, and number two is boiling. So this evaporation is occurring at every possible temperature. However, the evaporation rate can be enhanced or can be lowered, can be decreased. When you increase the temperature of the environment, the evaporation rate will be enhanced. However, when you decrease the temperature of the system, the evaporation rate will be lowered. While the boiling is actually boiling of a liquid occurs at a specific temperature when the vapor pressure of that liquid becomes equal to the pressure of the surrounding. So boiling uh, will be occurred at a specific temperature. However, evaporation is a surface phenomena that can be seen at every possible temperature that you can record. So the condensation is actually the reverse of vaporization. So it's a change of the physical state of the matter from the gaseous phase into the liquid phase. So thus the condensation can be taken as the reverse of the vaporization process. Vapor liquid equilibrium describes the distribution of chemical species between the vapor phase and a liquid phase. So the information collected from the vapor liquid equilibrium is very useful in designing the column for distillation, and the equilibrium vapor pressure of a liquid is generally strongly dependent on the temperature. So in distillation column, the separation of liquid mixture is done by the process of distillation, and this separation is based upon the volatility between the component. Greater the relative volatility, easier will be the separation. It means when two or three components, two or more than two components have very close volatility, so they are very difficult to separate one of them from that mixture. So when the components of the mixture have a wide range of volatility, they can easily be separated. In other terms, when they have different values of boiling point and the difference in the boiling point is very large, those components can easily be separated. However, when the components have very close value of boiling point, so they have a close relative volatility, so they are not easier to be separated from the liquid mixture. So this distillation process is used to separate component in a feed mixture based upon their relative boiling point. The lighter portion means that the compounds or the components that are more volatile and have low boiling point is in greater purity, and that will be collected in the top product stream, while the heavier fraction will contain those components with less volatile compound, and they will have a high boiling point. Those compound will be collected in the bottom product stream. This is the distillation principle which is involved in distillation column. Here three points are very important: A, B and C. Point A is designated to the liquid when it is heated, and the liquid state and its concentration remains same until this liquid reaches to the bubbling point. And after bubbling, when this mixture got uh, the bubbling point, and the sum of the component in the mixture, they will go into the vapor state, and the B state is representing the component of the mixture that turned into the turns into the vapors. That is a B state. Then from B to C, this is a uniform. This is the same composition. This composition is actually is in equilibrium. These B and C, this is the point where the the vapor molecules exist, and they separated from the liquid molecules. So molecules, they have low volatility, they remain in the liquid state for the longer time, and the molecules which have a higher boiling point, they will remain in the liquid state unless their boiling point reach reaches. However, the components of the mixer, they have they attained their boiling point earlier. They have low boiling point, they will go to the vapor phase, and molecules, they have the uh, higher volatility, they will go into the vapor phase. And this is the principle. The difference between the liquid and the vapor composition is a basis for the distillation process. So if there are three components or four components, there are multiple components in a mixture. So depending upon the boiling point and the volatility, those components will be separated out by using this distillation column. The distillation columns are divided into two categories: number one, batch columns; number two, continuous columns. In batch column operation, the feed of the column is introduced batch wise, and the frequency of the batch would be different. And after feeding the column, the distillation process begins. And when the required task will be achieved, the previous batch will be removed, and the fresh batch will be introduced into the column to start the fresh process in the content in the distillation column. While in the continuous column, which is the contrast to the batch column, continuous columns process a continuous feed stream. So a continuous feeding to the column will be processed. No interruptions occur unless there is a problem with the column or the surrounding process unit. So they are capable of handling high throughput and are most common type. So the continuous columns are most commonly preferred over batch column operations. Continuous column is further categorized into different groups depending upon the following uh, parameters, which are shown here in this slide. Number one, the nature of the feed that they are processing. It means that binary column or multiple component column. That column contains two components only, or a column can process uh, more than two components at a time. So if the column is processing two components, then this continuous column will be named as binary column, and if the column is processing more than two components, then it will be named as multi component column. And the second parameter which is important to classify the continuous column is a number of product streams they have. How many products are producing by the column? If the column is producing more than two products, then the continuous column will be named as multiple product column. And the third parameter, which is very important, this parameter is talking about the separation of the product. Number one is extractive distillation. This is the product which is retrieved from the bottom of the column. This product appears at the bottom of the column and it will be named as extractive distillation product. And the second product, which is usually obtained at the top of the column or top product stream, is azeotropic distillation. So these are three important parameters which are used to classify continuous columns into different categories. In this slide we will talk about the types of column internals. These column internals are responsible for the separation of different components that are processing in the distillation column. The first type is the tray column. In tray column, the trays of different designs are utilized to provide a platform for interaction between vapor and liquid. If the chances of interaction, if the frequency of interaction between vapors and liquid is increased, then better separation would be achieved by this mechanism. The second type is packed column. If we replace trays of the column with some packing material, the purpose of the introduction of this packing material in place of trays is to enhance the interaction between the vapors and the liquid. So which type of the column will you choose to get a better results? It depends upon the detailed cost analysis of the two types of the contactors. Contactor means that offers a contact place between vapors and liquid, and on the basis of qualitative analysis of relative advantages and disadvantages. So we will choose one of one of these two types will be depending upon the cost analysis, and will be depending upon the qualitative analysis of relative advantages and disadvantages. These are the parameters which helps us to select the column internals. Either it should be tray column internals or it should be packed column internals. The parameters are liquid dispersion difficulties. To disperse the liquid, this is the efficiency and the capability of the column internals to disperse the liquid into separate components, into different components. Number 2, capable of handling wide range of liquid rates. Number 3, cleaning. The column internals should be cleaned properly, and depending upon this, we select the column internals. Foaming and non-foaming systems. If the system that we are using or that we are going to process, it we should know about its properties. Either it's a foaming system or it's non-foaming system. So depending upon the system, it is either forming or non-forming, we select the column internals accordingly. And the periodic cleaning, which comes in the underline which comes under the cleaning parameter, weight of the column, design information, its dimensions, and interstage cooling, temperature change, and the diameter of the column. These are the parameters which will be taken into consideration while selecting the column internals. Okay, if you are using the non-forming system and the diameter of the column is greater than 0.67 millimeter 0.67 meter, then tray column will be utilized. And if the average temperature calculated for distillation column is higher than or equal to 98 degrees Celsius, then tray column will be preferred. And the plate contractor are actually the cross flow plates which are most commonly used as a plate contractor in the distillation. Contractor means the platform, the offering of a platform to provide an interaction, to provide a interaction between vapors and the liquid, in which liquid flows downward and vapor flows upward. In plate contactors, liquid usually flows downward and the vapor goes upward. The liquid move from plate to plate via downcomers. लिक्विड जो होता है वो डाउन कमर के साथ वो नीचे आता है अंडर द फोर्स ऑफ ग्रेविटी, एंड द सर्टन लेवल ऑफ लिक्विड इज मेंटेन्ड on the plate by wear. We must know what is wear. Wear is a small reservoir of water or solvent or the feed that you are having at the bottom of the column. So ये जो wear होता है एक छोटा सा डैम होता है, छोटा सा reservoir होता है जो आपके कॉलम के बॉटम पे होता है. So certain level of liquid is maintained on the plates by a wear. In previous slide we used two terms, trays and plates. Actually these trays and plates are the terms which are used interchangeably. So there are many types of trays design, but most common among them are listed here in this slide. Number one is a bubble cap tray, and the second one is a valve tray, which is also known as a floating cap, and the third one is sieve trays, is perforated. It means holes. These three commonly used trays will be discussed in the upcoming slides. A bubble cap tray has a riser or a chimney fitted over every hole and a cap that covers the riser. The cap is mounted so that there is a space between riser and cap to allow the passage of the vapor. Vapor rises through the chimney and is directed downward by the cap, finally discharging through slots in the cap and finally bubbling through the liquid on the tray. In valve trays, certain perforations, certain holes are present, and these perforations and holes are covered by liftable caps. Vapor flows lift the cap and thus self-creating a flow area for the passage of vapor. The lifting caps direct the vapor to flow horizontally into the liquid, thus providing a better mixing of the vapors and the liquid that is possible in these valve trays. The basic objective of the tray design is to provide an opportunity that can mix the vapor and the liquid in a better way. So the first type of the tray was the bubble cap tray. The bubble cap has a chimney and a cap. Through the chimney, the vapors goes upward, and the cap directs the vapors downward to interact with the liquid. While in the valve tray, there are liftable caps through which the vapors flow. The vapors lift the cap, and this is a self-creating flow area. And after passing vapor, the caps will direct the vapors to flow horizontally into the liquid, and is providing a better opportunity uh, of the mixing vapors with the liquid. And the third type, that is a sieve tray. Sieve trays actually are a simply metal plates with holes in them. Vapor passes straight upward through the liquid on the plate. The arrangement, number, and the sizes of the hole are design parameters. Because their efficiency, wide operation range, and ease of maintenance and the cost factor, sieves and valve trays have replaced the once highly through of the bubble cap tray in many applications. In this slide, we will compare the overall efficiency of the trays designs, three tray designs which we discussed in last slides. The first tray design is a bubble cap design, the second tray design is a valve caps, and the third one is a sieve tray designs. So we will compare in this slide the overall efficiency of three tray designs. We will put these following parameters: relative cost, pressure drop, efficiency, vapor capacity, and a typical turn down ratio. So when we compare the overall efficiency of these three uh, tray designs, the sieve trays offered best results for these parameters. So depending upon the results, depending upon this comparison of the tray design, sieve trays are found best to be utilized in uh, different distillation columns. Among different column internals, sieve trays are preferred due to the following reasons. Number one, the pressure drop is low is lower as compared to the other uh, column internals as well as the bubble cap trays. Their fundamentals are well established, which involve low risk in the distillation column operation. So the trays are in low cost relative to other types of trays, so they are cost effective, and they can easily be handled, and a wide range of wide variation are present in the flow rate. So they are lighter in weight, and it's easier and cheaper to install. Maintenance cost is reduced due to the ease of cleaning. Each tray has two conduits, two channels, one on each side, called downcomers. Liquid falls through the downcomer by the action of gravity from one tray to the one below it. A weir, which is a small dam, a small reservoir on the tray, ensures that there is always some liquid, it's hold up liquid on the tray, and is designed such that hold up is at a suitable height. And thirdly, being lighter, vapor flows upward to the column and is forced to pass through the liquid via opening of each tray. So these conduits, these uh, these tray columns will provide an opportunity of the interaction between the flow between the liquid and the vapors, and these conduits will serve as a downcomers, and there is a weir, there is a dam, there is a reservoir which is bottom of the tray column. That column that hold up liquid must be there at a suitable height. And the third parameter is the vapors which are lighter in weight, which have low boiling point. They will move upward to the column and will pass through the opening of the tray. This tray design will be serving as mini column, the column where the separation is going to be processed, accomplishing the separation task. So these mini columns are responsible for the task of separation of the component that present in the mixture. Number of trays is directly proportional to the degree of separation. So higher degree of separation will be achieved by having a large number of trays. So separation efficiency depends on the design of the tray, maximum vapor liquid content in the tray. So the maximum interaction between the vapor and liquid will give you the better efficiency. So better vapor liquid interaction approaches to better separation. So these trays will involve less energy uses and lower construction cost.